This quick podcast is going to deal with how to do equilibrium problems in terms of when you do a baby problem versus using ice. Okay, and there's key terms. Baby problems say things like, these are the values at equilibrium. Okay, so it's very simplistic. Not that ice is hard, but when a problem says things are found at equilibrium or values are measured at equilibrium, that's when you know you're doing a baby equilibrium problem. Ice has things like some things are put into a container. So they're placed into some kind of container or into a vessel. And then it says later on, or after equilibrium is reached. Okay, so in other words, initially there's these first conditions, and then later on equilibrium is reached. So in baby chem, you already are at equilibrium, and in ice problems, you are working towards finding out things that occur at equilibrium. So let's do two problems, actually three. Okay, so first, you're given the equilibrium constant. Okay, that's not always a factor. You may have to find the equilibrium constant, as we'll see. But what do you see here? When this is analyzed at equilibrium, oh, look at that, folks. It says at equilibrium. So what are keywords? At equilibrium, we just do a plain old baby problem. So it's analyzed at equilibrium. Concentrations of H2 and F2 are both 0.021. Okay, and by the way, I should have molarity here. Okay, and they want to know what the concentration of HF is. Well, what's the first thing you always do when you see equilibrium expression? You put a ratio of products to reactants. You write HF, and you square it because that's what your directions tell you to do. Draw your fraction line, put F2 and H2. Those are your directions. Now what goes in those directions? The values that they give you. And so what values are you given? You're given that K is equal to 2.1 times 10 to the 7th. You need to figure that out. They tell you right here. And what do you know about the value of K? Well, it's equal to what? HF. Do you know what HF is? You do not, do you? How do you know that? You're trying to find that out. What's the concentration of HF? So you're putting that in here. And if you'd like to, you can call that X. Okay, now I always like over here somewhere to say that the concentration is, by the way, that's a molarity, all right, of HF is, and this is my answer. Okay, so that's what I'm trying to find. Now, what do they tell me? Well, they tell me the molarity, don't they? They tell me the molarity for H2 and F2 are exactly the same. So I'm going to put 0.021 here, molar. If we don't write molar, you can. And 0.0021 molar. And if you don't write molar, you can. Okay? And so when I solve that and actually get a value, I go ahead and how do I do that? Let's go ahead and solve this math-wise. Don't I take this 0.021 and 0.021, I need to multiply them together and get them out of the bottom down here, don't I? So I need to go ahead and get rid of this here. Okay. To solve this, I need to say that 2.1 times 10 to the 7th times 0.0021 and 0021 is equal to x squared. Do you see how I get that? Okay. And then once I do that, I need to go ahead and take the square root, because to get x, I need to take the square root of this whole value right here. So everything multiplied together there, I need to square root that. And when I do, my value that I get is 0.096. And I don't care if you put a 0 in front or not. I don't like doing that, but that's what that is right there. And that's the answer you get when you do your math. So you either have questions on setting this up, or you have questions on how to do the math. Hopefully not both. Come see me. All right, now, let's do this. If an equilibrium constant is 45.9, so they tell you the value of K. Now be careful. I'm doing this on purpose. This is K Kelvin. That's a temperature. This is the equilibrium constant. that's equal to 45.9. That is not the same thing as the equilibrium, or excuse me, as the value for Kelvin. This is a temperature. Get rid of it. Okay? I know it's confusing because there's a capital letter K. So, capital letter K tells me what? Products to reactants. I'm going to go ahead and just write this right now, because I know I'm doing this kind of problem. So I'm going to go ahead and write these for my balanced equation. And what do I know? It says a particular equilibrium mixture. That means that you are doing these and this problem is at equilibrium, and so it's a baby problem. Okay? So I don't need to think anymore. I just go ahead and plug these values in. So what do I know? Oh look, these are in terms of atmospheres. So if I was really writing this and wanted to get extra credit on it, I could go ahead and put what right here. Let me rewrite this. So brackets are fine, okay, as far as I'm concerned, but you might see this in some kind of problem with parentheses. Why are the parentheses here? Because the parentheses, and it really doesn't matter which way I'm writing it. I'll write it the way I wrote it before, right? Order doesn't matter. On the bottom, and see I'm putting my brackets. Why am I putting parentheses? Because it's in terms of atmospheres. Remember I told you I give you extra credit, okay, if you're a Chem 1 kid. All right, now what do you know? You know that HI has a partial pressure of 4. So you're going to go ahead and put your 4 atmospheres up top, and you're going to square it, because that's what it tells you to do, your directions. You know your value for H2. What's your value for H2? 0.2 atmospheres. You don't know I2, so that's your X, isn't it? And what do you know? You know this is equal to 45.9. Now, where did I get these values from? This 4 atmospheres is my value for HI. That's why I put it right here. What else do I know? They give me the value of H2 at 2 atmospheres, and so that's why I put this right here. Do I know the value for I2? I do not. I want to know what the pressure of I2 is. And where did I get this 45.9 from? That 45.9 is coming from the fact that they told me the value of the equilibrium constant is 45.9. So now how do I solve? Well, I'm going to go ahead, make my erase a little bigger here so we can get rid of this a lot faster. I'm going to go ahead and take my math, okay, and I'm going to take 45.9 equals, I'll write it over here so you can see it better. Get rid of some of those zeros. Okay? So you ask yourself right now, where is X? Oh, X is in the bottom. What do you say to yourself? When X is in the bottom, you do the Faley flip. So, what's 4 squared? 4 times 4? That's 16, isn't it, on top? Okay? I'm going to go and take that X and that 45.9, and I'm just going to switch places. It works mathematically. Promise. And then I'm going to go ahead and solve. Okay? And when I solve, I get a pressure of 1.74 atmospheres. And that's the value for my, what's my X? My X is my I2. And that's my pressure, partial pressure of I2. That's why, guys, when I write these out, I don't like using X. That's just me. I like leaving it as I2, because then I remember what I'm solving for. Either that or you go ahead and label it in your answer right away, that you're finding atmospheres of I2. All right, now, let's compare this problem, and then I'm done. 4 moles of ammonia, NH3, is placed in a 2-liter container. Cool. At equilibrium, 2 moles of ammonia remains. What is the value of K? Well, does it say right here that this is placed in a container and the container's at equilibrium, or does it just say, hey, I put some stuff in a container? It says, hey, I put some stuff in a container, doesn't it? And then look what it says here. Later on, when equilibrium's reached, you have 2 moles left. So you have to be really careful when you read these. Okay, it doesn't say things start out nice and happy at equilibrium. Now you gotta remember, there's molarity. Now, the way you do these, and I've got a whole nother podcast that goes into this, but what I'm doing this for is so you can contrast and know when to do baby and when to do ice, okay? So, I'm going to go ahead and put 4 moles over 2 liters. And that's going to give me a molarity of 2. And I have none of this and none of this in my container. Why is that? Because all it tells me is I have 4 moles of ammonia placed in a 2-liter container. That's taken care of. Okay? Now, what's going to happen as equilibrium occurs? This is going to go down by x. How many? 2x, because there's a 2 here. This is going to go up by x. And by the way, why is this going down? Because it's reacting. Why are these both going up? Because they're forming. This is going to go up by x because there's a 1 out here. And this is going to go up by 3x because there's a 3 out here. That's my initial. This is my change. What's my value at equilibrium? Well, what's it tell me at equilibrium? It tells me I have 2 moles of ammonia left right here, doesn't it? Okay, 2 moles left. So that tells me I have 2 moles. And guess what? My container is still 2 liters, right? So what's my molarity that's left? I have 1 molar that's left, right? Now, what's true? How do I get that 1 molar? Well, I'm going to go ahead and I'm going to write this up here in black so that you can see what happens pattern-wise. And actually, let me go ahead and move this down, guys. Okay, so to get what my value is equilibrium, I'm going to go ahead and take 2 molar, write this value right here, and subtract 2x from it. What's my value here at equilibrium? X. What's my value here at equilibrium? 3x. Now, what did I just erase? I just erased what was left at equilibrium because they told me. They said, hey, look what I did. I measured that, look, there's 2 moles in a 2-liter container. So I know the value at equilibrium. And what do they want me to find? They want me to find the value of K. Well, how in the world do I do that? How do I find the value of K? Well, don't you have to write an equilibrium expression? Right? I don't know if I can grab that. Let's see. Yeah, I can. Let's get it out of here. Okay? So I'm going to write an equilibrium expression. And how do I do that? Well, K is equal to my products over my reactants and I'm going to go ahead and plug those values in. Now, I can't just put x's in. I actually need to find out what those values are. And so I need to find what K is. So what do I know right now? I know at equilibrium I have 1 molar of NH3, don't I? Right? It says I have 2 moles in a 2-liter container at equilibrium. So I know for a fact right now that I have 1 molar of this. And I'm going to go ahead and square it because that's what my directions tell me to do. Now, why is it cool I know what 1 molar is? I know that's 1 molar rather. Because now I know that this right here is equal to 1 molar. This value right here is equal to 1 molar. Okay, let me make that all black for you. Go back. Right? Isn't that equal to 1 molar? This value is equal to that. So knowing that, I can now solve for x. Okay? So what do you know? You know that 2 minus 2x is equal to 1. And so therefore, if you solve for this, you get x equal to 0.5. So x is equal to 0.5. Now you got to be really careful with this. The concentration at equilibrium is 1 molar for NH3. What did I just solve for? I just solved for 0.5 as being equal to x. That's going to help me find out these 2 values. So what is x? Well, x is equal to N2. Okay, so I'm going to put 0.5 up here. Why? Because I just figured out that x is equal to 0.5 and the value of this at equilibrium is x. What's this? This is equal to 3x. So 3 times 0.5 is 1.5, isn't it? And what am I going to do with that value? I'm going to cube it. How come? Because that's what my equilibrium expression up top tells me to do. Okay? So now that I know those, I can go ahead and solve. And when I solve, my value for K is 1.7.